A surface integral has the form double integral over s f of x, y, z ds. This is a surface integral over a scalar function, so f is lowercase. You notice it's a scalar function, not a vector. And the s over which we're integrating and the ds are both uppercase s's. We'll get into what it can mean in a minute, but here we're going to say if s, again uppercase, is a surface given by a vector equation r of uv is equal to x of uvi plus y of uvj plus z of uvk, then the surface integral is that double integral over s of f of x, y, z ds is equal to a double integral over d of f of r of uv times the magnitude of the cross product of the partial of r with respect to u and the partial of r with respect to v dA. Here d is a two-dimensional trace of s in a coordinate plane. And I just say a coordinate plane because it could be in the xy plane, xz plane, yz plane. It's a matter of convenience, or it's a matter of the setup that you're given. So that's the form of a surface integral. And something that's going to come up a few times here, ds is represented by this cross product of the partial of r with respect to u, partial of r with respect to v times dA. And in fact, you may recognize that as what came up when we did surface area. Now, just to point out a parallel, recall what a line integral looks like. The integral over c of f of x, y, z d lowercase s is equal to the integral from a to b of f of r of t times the magnitude of r prime of t dt. So what we're looking at with a surface integral is kind of like a higher dimensional version of a line integral. Now for the surface integral, if f of x, y, z is equal to 1, then we get the surface area. If f is equal to rho, say a density function, for a thin sheet, say of like aluminum foil, let's see the example the author gives, in the shape of S, then the result is a total mass of the sheet. So the meaning of a surface integral is, of course, context dependent. If the surface that we have is a function, so z is equal to g of xy, then we have the surface integral over x of f of x, y, z ds is then equal to the double integral over d of f of x, y, g of xy times the square root of the partial of z with respect to x squared plus the partial of z with respect to y squared plus 1 dA, and that should look familiar from surface area as well. And I should say for this, d is the projection of s onto the xy plane, in particular because we have this parameterized basically with x and y as the parameters. Similar representations exist if y was a function of x and z, for instance. Let's see what this looks like. Evaluate the surface integral over s of x, y, z ds. Now I'm going to pause right there. We know this is a surface integral because we have the uppercase s in our ds. S is given to be the cone with parametric equations x equals u times the cosine of v, y equals u times the sine of v, z equals u, and u goes from 0 to 1, v goes from 0 to pi over 2. Boy, I had that all needlessly crammed together. All right. Well, we need RU cross RV and its magnitude. So RU is equal to cosine of V, sine of V, 1. And our v is equal to negative u sine of v, u cosine of v, 0. Our u cross rv then is ijk cosine of v, sine of v1, negative u sine of v, u cosine of v, and 0. And you can verify that the answer here is going to be negative u cosine of v, negative u sine of v, u. You can also verify that the magnitude of ru, the partial of r with respect to u, I should say, cross the partial of r with respect to v is equal to u times the square root of 2. So, the surface integral over S of xyz ds is equal to the double integral over d of u cubed sine of v cosine of v. Now all of that comes from x times y times z from the definition that we have parameterizing in terms of u and v. ds is our u times the square root of 2 dA, and it's left for us to determine, given what d is, how we're going to deal with dA. Well, that's true in general. Here we were actually given that u goes from 0 to 1, v goes from 0 to pi over 2. So those bounds are going to give us our d here. So this becomes the square root of 2 times the integral from 0 to pi over 2 of the integral from 0 to 1, got lost there, of u to the 4th times the sine of v times the cosine of v du dv. This is a fairly straightforward integral, and the answer here is the square root of 2 over 10. I again leave it to you to verify that. Now you may be wondering here, u goes from 0 to 1, v goes from 0 to pi over 2. We have this u cosine of v. This is really the same thing as r and theta, right? R cosine theta, r sine theta. And so r would go from 0 to 1, theta would go from 0 to pi over 2. Just because it's u and v doesn't make that different, but the question would then be, why isn't dA r dr d theta, or u du dv in this case? The reason is, our parameter was originally in terms of u and v. We did not take a dA that was in x and y and then convert it to polar coordinates. So I'm going to make a note here. Since we did not convert to u and v, we don't have the equivalent of an r dr d theta. So if you're ever wondering, do I need an r dr d theta? Do I need to throw in the r? Well, ask yourself, did I convert from one coordinate system to another? If the answer is no, then the answer is no.